Hi, in this video I'm discussing Edexcel IAL Unit 4 January 2020 paper WPH1401 questions 1 to 13. In my next video I'll discuss the questions from 14 to 19. So if you want to get notifications when I upload the videos, I'll discuss other papers also. So when you want to get notifications when I upload the videos, it's better subscribe my video. So when you subscribe, you will get the notifications. Okay, now we'll go to the questions. Okay, so first question, Unit 4 paper, January 2020. A neutron can decay to produce a proton. Which of the following equations correctly shows neutron decay? So there are four different decay equations are given. We need to find the correct one. So the first one, the question one, the answer A says a neutron decays into proton, a positron, and an anti-electron neutrino. Okay, so here lepton number is not conserved. So if you think about the lepton number, neutron is a baryon, so its lepton number is 0. Proton is also a baryon, so its lepton number is 0. Positron is an anti-lepton, so its lepton number -1. Anti-electron neutrino -1. So you can say after decay, the total lepton number is -2. Before decay, lepton number is 0, not conserved. So invalid reaction. So the answer B, a neutron decays into proton, positron, and an electron. So here you can see the charge is not conserved. When you consider the charge, neutron is a neutral particle, charge will be 0. Proton is +1, positron is +1. Neutrino is a neutral particle, no charge. So the total charge after decay is +2, before decay is 0. So invalid reaction because charge is not conserved. When we see the answer D, then I'll come to the answer C. Answer D, the fourth answer, a neutron decays into proton, electron, and a neutrino, electron neutrino. So there also, you can see that lepton number is not conserved. When you think about the lepton number, neutron is 0, proton is 0 because both are baryons. Lepton number of a baryon is 0, you know that. So electron is a lepton, so +1. Neutrino, electron neutrino is also a lepton, +1. So the total lepton number after decay will be equal to +2, before decay 0, not conserved. So the only valid reaction, answer C, where all the factors are conserved. So the correct answer for question 1 is C. Okay, question number 2. At distance d from a point charge of magnitude q, the potential is V. Which of the following is the potential at a distance 4d from a point charge of magnitude 2q? So we know the equation for the potential of a point charge, which is given by V equal kq over r. So we know this equation is given in the data sheet. So V equal kq over r. So I can say V equal kq over d. The distance is d. So there is another charge that is 2q. What is the potential at 4d? I need to find the potential in terms of V. So I can say V1, the new potential, V1 is equal to k times 2q over 4d. I'm using the equation V equal kq over r. It's a standard equation given in the data sheet. So for the charge 2q, the charge q is 2q, the distance is 4d. I need to find the potential at 4d. So solve this one. I can get kq over 2, 4 will get cancelled. So it will become half times kq over d. That will be V by 2. So the potential will be V by 2. The correct answer B. Question number 2. Correct answer B. Question number 3. A ball of mass m traveling with velocity. The word used, velocity. V strikes a wall at right angles. It bounces off the wall in the opposite direction at the same speed. Careful the words they are using. Earlier they are saying velocity V, then they are saying same speed. So that means when it bounces back, the velocity will be minus V. So I can say, if I draw a diagram, question number 3, a ball is moving at a velocity V, shall take initial velocity towards right, which is positive. So the question paper is giving the initial velocity as v with positive sign. So positive is not marked, but we know positive is not marked means it's positive. This is the wall. This is before collision. After collision, the ball is bouncing back with the same speed, means opposite direction. So towards right is taken positive, means this will be negative v. We know that during collision, the ball will experience force towards left. According to my diagram, the wall will experience force towards right. So for the question is, find the, they are giving four answers. Which of the following is the impulse on the wall? You know the impulse, I is equal to Ft, that is equal to mv minus mu. So for the ball, the direction of impulse is same as the direction of the resultant force acting on it during the collision, which is towards left for the ball. For the wall, it will be towards right. That means the direction of the impulse on the ball is towards left, which is negative sign, because according to the sign convention they are using, the impulse on the wall will be towards right, that will be positive sign. Okay, so we can't find the impulse for the wall directly. We don't have any equation because wall is not moving, but we have to find the impulse on the ball. Because ball is moving, we know the changing momentum of the ball. From that we can find the impulse for the ball. According to Newton's third law, the same force is acting on the wall for the same time period. So Ft will be the same for the wall also. So the impulse will have the same magnitude but opposite direction, which is towards right. Okay, so I can say for the ball, I know the impulse for the ball is towards left. So I'm taking towards left impulse for the ball, that is going to be towards left. I am taking it. So mv, so the m into the final velocity is negative minus initial velocity towards right. So I am taking towards left positive. I know towards right is positive. So minus mv. So it's going to be minus 2 mv for the ball. The impulse for the ball towards left is minus 2 mv. Therefore, same magnitude of impulse on the wall towards right. Towards right is given positive according to the question. So impulse on the wall equal to mv, which is positive, means towards right. So the correct answer B. The correct answer B. Question number 4, you can see the diagram. All the potentials are given with positive sign. That means positive sign is not marked, but it's positive. We know that 6 volt, 4 volt, and 2 volt all are positive values. So which of the following diagrams show a possible combination of electric field? So it's actually due to a circular equipotential surface, means that's only due to the point charges. Point charge, remember that for point charges, the equipotential surfaces are always spherical shape. Because your electric field lines are radial, always equipotential surfaces are perpendicular to the electric field lines. Means if you draw an equipotential surface which is perpendicular to the radial field of a point charge, the equipotential surface will become sphere. But when you draw on 2 dimensions, it becomes circle. So the charge is a point charge. We know it's positive charge because all the equipotential surfaces are shown with positive value. When we are calculating the electric potential for a point charge by using V equal KQ over R, we must use the sign of the charge. That means the electric potential of a negative charge will be negative. Positive charge, electric potential will be positive. When we are using the equation, we should include the sign of the charge. Here all the potentials are given with positive value, means it is a point charge which is a positive charge. So we know that electric field lines are radial away from the charge. So the correct answer A. So question number 4, answer A. Question 5, parallel plates are shown. So question 5, So this is plus 10 volt, this is 0 volt. That means relative to this plate, this is negative. This is negative. Negative is not marked. 0 volt means it's earth, or relative to this voltage is lower than 10 volt means it's negative 10. Or you can say relative to this is positive means relative to this is negative. So the electric field lines, you know that always from positive plate to the negative plate. So the direction of the electric field lines will be downwards. We know that it's going to produce an uniform electric field downward direction. So the question is, point X is midway between the plates. Which of the following is the electric field strength? So it's a uniform electric field. So if we find the electric field in this region, that is given by E equal V over D, we can use this equation only for uniform electric field. We know the potential difference between the plates 10 minus 0. That's the potential difference. These are the potentials given 10 and 0. And the distance between the plates is 20 centimeters, 0.20 meters. So solve it, you will get 50 volt per meter. The direction downwards. So answer B, correct answer B. Okay, question 6. A gamma photon of energy 18 mega electron volt produces a particle and its antiparticle. That is called pair production. That interaction is called pair production. Which of the following will give a maximum? The word maximum is used. Maximum possible mass of the particle in kilograms. So you know mass of a particle and the mass of its own antiparticle will be the same. So here I can write the reaction equation. So question number 6. A photon decays into a particle X and its antiparticle. So the reaction equation is shown. What's the energy equation? Mass energy. During pair production, during annihilation, mass alone will not be conserved. Energy alone will not be conserved. So the physical quantity which is conserved is total mass energy. So photon has no mass. Its energy, we know that I can say energy of the photon, I'll say capital E, that is equal to mass of X, its equivalent energy. So I'm going to equate the total mass energy. So particle X, its mass, if I take mx into c square is the equivalent energy of its mass. It might have kinetic energy. I'll put kinetic energy of X. Plus, same way, mass of X dash, same as mass of X. Mass of X dash also has equivalent energy. That will be mx bar, the antiparticle, mx bar c square. Its kinetic energy, I can say kex bar. Okay, so mass of X and mass of X bar are the same. So I can write this 2 times mass of X c square plus kinetic energy of X plus kinetic energy of X bar. So we need to find the maximum mass. We'll continue 2 times mass of X c square equal to energy of the photon minus kinetic energy of X plus kinetic energy of X bar. Okay, so we know to get mx. So if I want to get mx, that is going to be E minus kinetic energy of X plus kinetic energy of X bar over 2c squared. Okay. Now I need to get the maximum mass, the word maximum mass of the particle. So to get the maximum mass, kinetic energy of X and kinetic energy of X bar, the kinetic energy of the particle and the kinetic energy of the antiparticle must be equal to 0. That means they are just created without any motion. So if they have, for the given energy of the photon E, during the pair production, if the particle and antiparticle pair just created without any kinetic energy, means the mass will be the maximum. So when this quantity becomes equal to 0, we will get the maximum mass. I can say mx maximum we get when all these becomes equal to 0. So that means energy over 2c squared. So now substitute energy, we know that given as 18 mega electron volt. To find the mass in kilogram, I need to convert the mega electron volt to joule. So 18 mega 10 to the power 6 electron volt 1.6 10 to the power minus 19 over 2 times 3 into 10 to the power 8 all this square. So when you solve 8 into, it will become 9. So finally, you will get the answer 9 into 10 to the power 6 into 1.6 10 to the power minus 19 over 3 into 10 to the power 8 all the square. This is the maximum mass of particle X that happens only when both the kinetic energy of both X and X bar becomes equal to 0. So that's the maximum mass. The correct answer D. Okay, question number 7. A diagram something like this is given. A current carrying wire is placed between two magnetic poles as shown. The magnetic flux density in the region between the poles is 0.70 Tesla. Which of the following gives the magnitude of the force on the wire? Okay, so here we know that the field lines will be from north to south. We know the equation for the force F equal VIL sine theta, where theta is the angle between the direction of the magnetic field and the direction of the current flow. So here we know this length is given 6.5 centimeters and this length is given 5.5 centimeters. So the angle between the magnetic field and the direction of current, that is this angle theta. So if I use this angle theta, so I can draw again. This is the length of the rod, 6.5 centimeter. And this length we know that is 5 centimeter. I need to find this angle theta, the angle between the magnetic field and the current. So sine theta equal to 5 over 6.5. That is the sine theta. So we need to find the F equal VIL sine theta. The question is the force acting on it. We know the V, that is that I can write in 5 and 6.5 should be in meters. But anyway, numerator, denominator 10 to the power minus 2 will get cancelled. So that's the reason I didn't write that. So F equal VIL sine theta. So here the magnetic field strength is 0.070. The current flow is given as 1.5 amperes. 1.5 amperes. The length of the rod is 6.5 into 10 to the power minus 2 into sine theta, again 5 into 10 to the power minus 2 over 6.5 10 to the power minus 2. Okay, so when you solve, you will see that 6.5 10 to the power minus 2, 6.5 10 to the power minus 2 will get cancelled. So finally, you will get the answer into 5 into 10 to the power minus 2 or 0.05. 0.05. So the answer 0.070, 1.5, 0.50. So either answer A or C. Now we need to find the direction of the force. So we know the magnetic field is downwards. Use the Fleming's left-hand rule. Magnetic field is downwards. The component which is perpendicular to the rod, the magnetic field component which is perpendicular to the rod will be this way. This is the direction of the magnetic field which is perpendicular to the rod. Use the Fleming's left-hand rule. Magnetic field downwards. Magnetic field downwards. The component which is perpendicular will be this direction. So the direction of the current is upward. So the current is this direction. You can use the current this direction. Magnetic field, current is this direction along this way. Magnetic field is downwards. The force will be out of the page. Use the left-hand rule. You will see the thumb will point out of the page. The force will be out of the page. So correct answer is C. It's easy to do it on the notebook rather than on the board. So use the Fleming's left-hand rule. This is red color line, which is the component of the magnetic field perpendicular to the rod. So use the Fleming's left-hand rule. The thumb will point out of the page. The direction of the current is along this direction. This is the direction of the current given. So correct answer, this numerical value with out of the page. So correct answer C. Okay, question number 8. Point charges plus Q and minus Q, this is positive Q, plus Q and minus Q, are placed at X and Y respectively. When another charge is placed at Z here, the resultant force on the charge at X is becoming 0. Distance XY is equal to YZ. Which of the following is the charge placed at Z? Okay, so now the force, before you place the charge at Z, these two charges will interact and the charge Q will have electrostatic force due to negative Q. It will be an attractive force. So the force on Q will be towards right. I'll call it as F1. Now, when you keep a charge at Z, this force F1 is balanced, means the charge Q should experience a force opposite to F1. So this must be a positive charge, let it be Q. Then that should be towards left, I'll call F2. F1 must be equal to F2. Then only the resultant force acting on it will become equal to 0. The distances are same. These two distances I can call R, R. So, okay, I need to find the value of, I need to find the charge Q in terms of symbol Q. So, I can say F1 equal F2. So, F1 is equal to K, Q, this also numerical value same, Q over, I don't need to put the minus sign. So, I know the numerical value. I'm considering the numerical values, but I know the directions opposite F1, F2. So, K, Q1, Q2 over, Q into Q over R squared. That is F1. F2, K, this charge is Q into Q. This Q I need to find it over. R squared is distance 2R. R plus R, 2R, all things squared. Okay, I need to find the Q. So here K will get cancelled. This Q and this Q get cancelled. Here 4R squared, R will get cancelled. So I'll get Q is equal to Q over 4. So Q should be 4Q. Correct answer D. Question number 8. Correct answer D. Okay, question 9. The diagram shows the momenta P and Q of two bodies about to collide. So before collision, the momenta are shown like this on the paper. When the bodies collide, they merge and move on a single body. So you know, if we find the resultant vector of these two vectors, you know momentum is a vector. If I find the resultant vector by considering the vector addition rule, the direction of the resultant vector will be the final vector for the total momentum after collision. So after collision, they are joining together, merge together, and move means according to law of conservation of momentum, that momentum after collision must be same as the resultant of these two vectors, these two momenta. So the only possible resultant, I can draw two different ways. If I want, I can continue this P like this. I can draw parallel to this line P. And Q, you know the vector addition rule says tip to tail. That means from the end of the first vector, you should continue the second vector. So the Q should be like this. So the resultant could be something like this. We don't know the magnitude, so the resultant could be this one. So that means the total momentum after collision should be like this. Or I can draw a diagram. If I draw the Q like this, first if I draw the Q, and if I draw the P later, resultant should be like this. So only these two diagrams, vector diagrams, are the correct one to get the total momentum after collision. That will be same as total momentum before collision. So the correct diagram is C. The diagram C represents this one. So this is the correct answer. Question number 9, correct answer C. Question 10. In an electron deflection tube, electrons are released by passing a current through a metal filament. What is the name given for this process? We know that thermionic emission. So, you know, when certain metals are heated, they absorb the heat thermal energy, and atoms will vibrate. Due to vibrations, electrons will be released. That is delocalized electrons will be released. That is called thermionic emission. So question number 10, correct answer, D. Okay, that's the end of MCQ questions. Now we'll go to the section B, question number 11. You know, in this video, I'm discussing questions 1 to 13, and the next video in which I'll discuss questions 14 to 19. Okay, question number 11. This reaction is given. A section from a periodic table is shown. Technetium Tc produced when a deuterium ion. You know, deuterium is one of the isotope of hydrogen, so it consists of one proton, one neutron. So its mass number will be equal to 2. So deuterium ion collides with the nucleus of one of the other elements shown in the table. In this process, a number of neutrons are also released. So we need to find out how many neutrons are released. We need to find out by balancing the reaction equation. Deuterium is an isotope of hydrogen with one proton, one neutron. So mass number will be 2. Complete the nuclear equation. Okay, so to complete it, we know that what to put here, we need to identify that. So they are saying a technetium is produced when a deuterium ion collides with a nucleus of one of the other elements. So after balancing it, we need to identify which element is it by using the atomic number. We'll see. So we know that deuterium means mass number 2, atomic number 1. It should be balanced. Okay, so here the mass number is 96, here 2, so that is total 98, here 95. Neutron, we must know its mass number or baryon number 1. What we put here is the charge, which is 0 for particles. What we write for particles, what we write up is the baryon number. What we write here is the charge, right? For nucleus, what we write on the top will be the mass number, bottom will be the atomic number. For particles, baryon number and charge, you know, neutron charge is 0. So to balance it, we know 98, this is 95, means only thing we need to put 3 here. 3 neutrons are created. Okay, so when we balance the atomic number, here we can find out, we need to find the atomic number. That's going to be 43. This is 0. Here 1 means it should be 42. So atomic number 42, which element? See the table. With atomic number 42, there's only one element, that is molybdenum. So MO. Okay, so question number 12. The following passage is taken from an article about the history of particle physics. Mystery particles. By 1932, scientists knew of the existence of subatomic particles, the electron, the proton, and neutron. These were believed to be fundamental particles. So you know fundamental particle means particle that has no internal structure, or we can say the particle that cannot be splitted further is called fundamental particle. In 1936, scientists were using TRAC's cosmic rays to identify the predicted particles known as mesons. Instead, another particle was discovered, the muon. This was so surprising that Nobel Prize winning physicist Isel Rabi said, "Who ordered that?" Describe how the underlined particles fit into the standard model. So here actually nothing. You have to say something related to standard model and the particle stated in this question. So here you can say like this. First, let us say what is fundamental particle. So they are saying that in the given small paragraph, the second line, these were believed to be fundamental particles. So you should say what is fundamental particles. Then you can say electron, muon, both are fundamental particles and both belong to the group called leptons. Then you can say proton and neutron are not fundamental particles. They are called baryons. They are made up of 3 quarks, you can say that. Then you can say meson is also not a fundamental particle. It's made of quark and an antiquark, you can say. So then you can say about internal structure of proton and neutron. They are made of Proton is made of two up quarks and a down quark. Neutron is made of two down quarks and an up quark. That's all. So you can tell something more about generation. You know, generation means you can see all the books when the when you think about up quark, down quark, strange quark, charm quark, bottom quark, top quark. Those are the six quarks in the order of the mass. So electron, electron, neutron, muon, muon, neutrino, tau, tau, neutron. Those are the leptons. So you can see that in that order, the first two are in quarks. You can say up quark and down quark are first generation. Then strange quark and charm quark are second generation. Then bottom and top are third generation. So also you can see the mass will increase from up quark to top quark. You know, quarks are actually, when you think about up quark and down quark, they exist in the form of protons and neutrons. So I can, or otherwise I can say protons and neutrons consist of up quark and down quark. So other quarks, when you think about strange quark, charm quark, bottom and top quarks, where can we find them? Actually, they are created in the particle accelerators. When the accelerated particles collide, the energy carried by the particles are used to create these quarks. And quarks never exist alone. You can't see the track of a quark. Actually, quarks always in a group format, like three quarks together called baryon, three antiquarks together called antibaryon, or quark and antiquark together called meson, or another model that is called pentaquark. So that's the only possible combination of quarks. So whatever the track they find on by using the particle detectors are not the tracks of the quarks, because quarks never exist alone. They are always in groups. I already told baryon, antibaryon, meson, and pentaquark. So the tracks what we see are the tracks of the either baryon or meson or antibaryon or pentaquark. So quarks alone, they never produce tracks because they can't exist alone. So actually, how do they identify quarks then? There's a method called eightfold way, not in your syllabus, not in the A-level syllabus. Edexcel, Cambridge, even in National Baccalaureate, they don't have these things. But anyway, so we can say eightfold way is a method. Actually, it's actually an organizational scheme of work just used to identify the development of quark models. Actually, it's a very complicated method. So what the tracks they find based on quarks are the tracks of either baryon or antibaryon or meson or pentaquark. So from those tracks, they identify the internal structure of those particles and they found they are the quarks. Okay, so anyway, not much necessary about this eightfold way. So here we can write the answer like this. Okay, so this is the answer for question number 12. Nothing new, just basic thing. Yeah. Okay, question number 13. So there's a diagram of a toy is given. The head is pushed down onto the base, compressing a spring. When released, the spring expands and the toy jumps into air. A student investigated the toy. The student placed the toy on a balance. To measure the force required to compress the spring, the force was 14 Newton when the spring was fully compressed by 1.7 centimeter. When the toy was launched, it jumped to a height of 1.5 meters. So A part showed that the maximum energy stored in the compressed spring was about 0.1 joule. So you know this unit 1. So when a spring is compressed, work is done on it. So energy stored in the spring is the elastic potential energy. That is given by half F delta X. So here we know the force that we applied, that is 14 Newton, and the delta X is the compression, that is 1.7 centimeter. So substitute the values, you will get the answer. So question 13, A part, the energy stored in it, so that is the elastic potential energy. So half F delta X, so the force is 14 Newton. The compression 1.7 centimeter converted meter 10 to the power minus 2 joules. Solve it. You will get that will be 0.119 joules, approximately 0.1 joules or 0.12 joules. So they also show it's approximately 0.1 joules, so 0.1, but we can say 0.12 joules. Okay, so B part. Initially, the spring was fully compressed as the toy was released. The head accelerated upward on its when the accelerated upwards on its own until the spring was uncompressed. So when the until the spring becomes to the natural length, the head is moving along. The diagram is shown. The head then pulled the base upwards and they moved together at the same speed. Okay, so the question here is something related to momentum. So what's happening when the head is compressed? So that means it's like initially this is the base. So the head is here. So initially the spring is like this. You are compressing it, something like this. And when you released it, you know the head will move up. When the head moves up, when the head comes back to the natural length of the spring, it will pull the base also. So actually here, the total momentum is conserved. That's what we are going to do in the part B. They're asking to find whether the momentum is conserved. So normally in your questions, most of the past papers, we came across questions related to momentum. Either there will be collisions or explosions. But this is not a collision, but also it's not an explosion. Here something like jerk, we can say jerk or sudden impulse is exerted on a string. Say for example, if you have two spheres, something like imagine a sphere of mass m1 is kept on floor and you are having another mass m2, it is connected by a string of length maybe 1 meters. Okay, initially you are holding the M2 closer to M1. This is the ground. You are holding the M2 closer to M1 and you are throwing it vertically upwards. And imagine the string, this string is inelastic string. So when the M2 moves to a height of 1 meter, when it comes to 1 meter, so at that moment, just before the string becomes stretched, it's inelastic. That means stretched means when the string reaches its natural length, which is 1 meter, just before it reaches the natural length, its speed could be u1. Then what happened? When the string will pull this also, there will be tension. Just before the tension becomes positive value, that means when the string is slacked, there is no tension. So when this sphere, which is mass m2, just moves almost 1 meter, little smaller than 1 meter, the speed is u1. This is still at rest. But when the length of the string becomes 1 meter, when it returns to the original initial length, there will be tension on it. So it's going to pull the second sphere m1 also upward direction. Since the string is inelastic, both when there is tension at that moment, both spheres will have the same velocity v1. Okay, so just before this is at rest now, I can say this is at rest, u2 equal to 0. Just before the length of the string becomes 1 meter, the velocity of this sphere is u1, no tension. Now there is tension, the string has returned its original length, there is tension but inelastic string. So both should move together because otherwise string will break, but string is not snapping. So they should move at the same velocity. That velocity v1, if I say, I can use law of conservation of momentum here. because when I consider this as a closed system, there is no other external force, because the string has the tension exerted by the string on the M2 will be downwards. If you draw the free body force diagram, the tension acting on M2 will be downwards, tension acting on M1 will be upward direction. So they are in opposite direction. So closed system, I can use the law of conservation of momentum here. So if I write the law of conservation of momentum for this situation, I can say momentum before the string returns to original shape, or when the string is little bit stretched, the initial momentum m2u1 plus 0, this is at rest, should be equal to, they are going to move together at that moment, that is m1 plus m2 v1. I can use the law of conservation of momentum. So in this question also, they ask me to check whether the momentum is conserved, determine whether toy obeys the law of conservation of momentum. Yes, we know that with the head returned to the original, when the spring returned to the original shape, the spring going to pull the base also. So both the head and the base are moving together. So here also the law of conservation of momentum is valid. Anyway, they have given the numerical values. By substituting, we are going to show the momentum is conserved. Okay, so momentum is conserved, not only collision, not only explosion, even this type of motion also, total momentum is conserved. Okay, so B part, initially the spring was fully compressed. As the toy was released, the head accelerated upwards on its own until the spring was uncompressed. The head then pulled the base upwards and they moved together at the same speed. So the head only moving upwards until the spring returns to its original shape, that is uncompressed. So the student used the elastic potential energy stored in the spring to determine the maximum speed of the head. So actually initially the head was compressed and released. So until the spring returns to its original length, all the elastic potential stored in the spring will be given to the head in the form of kinetic energy. So we'll find the speed of the head just before it pulls the base of the toy, right? So we will find that one first. So B part, question number 13, B part, we can find by using law of conservation energy, loss in elastic potential energy equal gain in kinetic energy. By using that, we can find the speed of the head alone when the spring returns to its original length, or when the spring has no compression. Until that, the elastic potential energy will be transferred to the head in the form of kinetic energy. So I can say loss in elastic potential energy equal gain in kinetic energy of the head. So we already found the elastic potential energy. We know that 0.119 119 is the actual value. 0.119 is equal to half m, that mass of the head is given. So that is given as 66.4 grams. So half into 6.4 gram convert to kilogram into, I can say u1 square. u1 square is the speed of the head when the spring just returns to its original length. The head was initially at rest when it was released from the maximum compressive position. So we'll find the u1 from here. u1 is the speed of the head just before it pulls the base of the toy. So you will get u1 is equal to 6.10 meter per second. Okay, now what's going to happen? When the head little move further, it's going to stretch the spring. So when the spring is stretched, the base also will be pulled up. Now both the head and the base with the spring together, the complete toy will move upwards. Here momentum will be conserved. So I can find the initial momentum of the head alone. So I'll find it first. Initial, sorry. So its mass 6.4 grams. So that will be 6.4 into 10 to the power minus 3 into 6.10. That's the initial momentum. We'll find that one. That will be 0.0390 kilogram meter per second. Okay, that's the initial momentum of the head. Now I need to find the speed at which, so that means when the head stretches the spring, the whole system is going to move and the base is going to leave the ground. What will be the speed when the spring gets tension? That is the, we can say something like after the spring becomes stretched at that moment, what is the total speed of the, what's the speed of the whole system? We need to find it. So that we can find by using loss in kinetic energy equal gain in gravitational potential energy for the whole system. So I can say for the whole system, for the whole toy, I can say for the whole toy, loss in kinetic energy equal to gain in gravitational potential energy. Okay, so there I need to, I'm going to find the speed at which the whole system or the toy left the ground, left the table or ground, whatever it is. So there I can say loss in kinetic energy means I can say half into mass of the toy is 7.2 10 to the power minus 3 times, I call it as V1 squared. The speed immediately after the spring is stretched, the speed is V1. Both head and the base will have the same speed, V1. So half m V1 squared is equal to gain in gravitational potential. So mass, same anyway, it's going to get cancelled. 7.2 10 to the power minus 3, 9.81, and it jumped to 1.5 meters. So we will find the V1 here. So V1 will be equal to, we will get 5.425 meter per second. So final momentum of the toy when the spring is stretched. Equal to mass of the whole system, that is 7.2 10 to the power minus 3 into speed of the whole system 5.425. So you will get the same answer 0.0390 kilogram meter per second. Or you can say 3 decimal point 0.039 kilogram meter per second. So you can see this momentum and this momentum are the same, means total momentum is conserved when the spring is stretched. So the C part determined whether kinetic energy was conserved that the head began to pull the base upwards. So will there be the kinetic energy conserved? We'll find it. So the initial kinetic energy of the head just before it pulls the base is same as the elastic potential energy stored in the spring. So I don't need to calculate. So I can say C part initial kinetic energy of the head just before it pulls the it pulls the base. We already found it, that is equal to elastic potential energy stored in the spring, that is 0.119 joules. Final total kinetic energy is equal to half into mass of the whole system, the toy 7.2, 10 to the power minus 3, into the speed we found it 5.425 square. So that will be 0.106 joules. So you can see that the total kinetic energy after or when the spring is stretched is less than the initial kinetic energy of the head. So maybe some of the kinetic energy would have converted to heat uh, in the spring. So that's the reason in this process, the total kinetic energy is not conserved. You can give the conclusion total kinetic energy is not conserved. Okay, so that's the end of question number 13. So I told I will discuss from question 14 to question 19 on my next video. The link or the URL for that video will be given in the description of this video. You know the description, you can find it below the video. There's the icon like this. There, if you click it, you can get the URL or the link for the next video. And if you want to get more videos, I'm uploading other units also. If you want to get the notifications, it's better to subscribe. If you subscribe, you will get the notifications when I upload the other videos. Okay, right, bye.